The top 200 meters of the ocean, the epipelagic zone, is the marine environment we know best. Up here, sunlight easily penetrates the water, feeding the microscopic phytoplankton that drift on the currents and drive the entire marine food chain. It's a familiar layer, full of light, motion, and warmth. But if you look at this vertical scale model, that sunlit layer is incredibly thin. Directly beneath it is a sheer, nearly 11,000-meter drop down into the abyss, bottoming out at the Challenger Deep in the Mariana Trench. Descending into this void means facing hostile extremes. The water temperature plunges to near freezing, sunlight drops to absolute zero, and the sheer weight of the ocean above creates physical pressures over 1,000 times greater than what we feel at sea level. That is enough mechanical force to instantly crush a standard submarine. For decades, scientists assumed these extreme depths were entirely barren. Yet, exploring this dark water reveals how biology can engineer brilliant, highly specialized solutions to survive environments that should theoretically destroy living tissue. As we drop into the mesopelagic, or twilight zone, this color spectrum graphic shows exactly how sunlight is physically filtered out of the water. The deeper we go, the more the water absorbs longer wavelengths of light. Warmer colors like reds, oranges, and yellows vanish entirely, leaving behind only a scattering, faint blue glow. In this dim environment, staying hidden requires producing your own light. Keeping our eyes on this same diagram, watch the dark silhouette of the lanternfish. It becomes completely invisible from below by emitting a soft glow from specialized organs on its underbelly. By matching the exact brightness of the downwelling sunlight, it erases its own shadow, a tactic biologists call counter-illumination. While some animals use bioluminescence as a cloaking device, others use it as an offensive weapon. The anglerfish dangles a glowing, fleshy lure directly in front of its razor-sharp teeth, using the allure of light in the darkness to draw unsuspecting prey straight into an ambush. Surviving the twilight zone also forces bizarre forms of cooperation. The siphonophore moves like a single graceful ribbon of jellyfish suspended in the dark, but it is actually a living colony. It is composed of thousands of genetically identical clones, called zooids, that divide up specific survival tasks. Some are built exclusively with stinging tentacles to catch food, while others exist entirely to reproduce or defend the structure. Where the sun can no longer provide energy, organisms adapt by manufacturing their own. They turn self-generated light into biological camouflage and deadly traps, sacrificing individual autonomy to build efficient colonies. Past 1,000 meters, we cross into the midnight zone. Here, photosynthesis stops entirely, and the ocean is plunged into absolute, permanent darkness. It is also here that the physical weight of the water becomes intensely dangerous. Shallow water fish rely on air-filled swim bladders to float, but at over 100 atmospheres of pressure, those rigid pockets of air would instantly collapse inward under the immense weight. This microscopic view reveals how deep-sea biology solves the pressure problem. Their cells are packed with special molecules called piezolites. These act like tiny internal support beams, physically reinforcing the cell membranes so proteins don't crumple. To maintain buoyancy without air, animals construct their bodies from incompressible fats and flexible, watery tissues. Finding food in this void requires immense patience. The primary energy source is what scientists call marine snow, a sparse, slow rain of dead plankton, waste, and organic debris drifting down from the sunlit waters thousands of meters above. Because meals are incredibly rare, deep-sea predators must maximize every single opportunity. The black swallower uses a highly expandable body to consume other fish up to twice its own length and 10 times its weight, stretching its stomach so wide that the outer tissue becomes practically transparent. By abandoning rigid bones and air pockets for watery, flexible tissues, and evolving the capacity to hoard massive, infrequent meals, animals in the midnight zone have engineered their bodies around the physical constraints of the deep. Miles below the surface, the descent finally reaches the abyssal plain. This freezing, entirely flat expanse of seafloor covers roughly half of the Earth's total surface area. Scarcity rules down here, making the death of a large surface mammal a critical biological event. When a whale carcass sinks to the seafloor, a phenomenon known as a whale fall, it delivers decades worth of concentrated energy all at once. This massive influx of food triggers a sudden swarm of deep-sea scavengers, rapidly stripping the carcass down to the bone. The ecosystem thrives even after the meat is gone. Specialized bacteria break down stored lipids deep inside the whale skeleton. This chemical process releases sulfides, which in turn provide energy for a dense microbial community that can survive on the bones for decades. But the abyssal plain is not the deepest point. As this cross-section diagram shows, immense geological pressure is at work where the heavy Pacific tectonic plate slowly grinds beneath the smaller Mariana plate. This process, called subduction, forcefully drags the edge of the crust downward, carving out a massive V-shaped depression, the Mariana Trench. At the very bottom of this trench lies the Challenger Deep, nearly 11,000 meters down. Here, tiny crustaceans called amphipods endure 1,000 atmospheres of pressure. They survive by secreting a specialized aluminum-based gel, physically armoring their exoskeletons against the crushing weight of the ocean above them. Removed from the sun's warmth, life at the absolute bottom refuses to be completely crushed, relying on sudden geological windfalls for food and literal metal armor to withstand the relentless mechanical force of the deep. For centuries, mapping this underwater terrain meant blindly dropping weighted ropes over the side of a ship and counting the length. That changed in the 20th century with the invention of sonar, allowing researchers to bounce acoustic sound waves off the seafloor to calculate extreme depths with precision. In 1960, humans proved they could physically visit these extremes. Swiss engineer Jacques Piccard and U.S. Navy officer Don Walsh spent 5 hours descending to the floor of the Challenger Deep inside the Trieste, a heavily armored, massive bathyscaphe engineered to survive the brutal journey. Over 50 years later, modern engineering allowed for a return. In 2012, filmmaker James Cameron completed a solo dive to the same remote location, piloting the highly specialized, vertically oriented deep-sea Challenger submersible directly to the trench floor. Yet, despite these massive leaps in acoustic mapping and deep-sea engineering, only about a quarter of our global seafloor has ever been mapped in high resolution. As autonomous underwater drones prepare to map the rest of the abyss by 2030, the deepest layers of our ocean stand as a final frontier. The dark waters below contain unmapped geology, alien biological adaptations, and critical data about the long-term carbon cycles of our planet, all waiting to be brought to light.